these are not light which are visible, what you are dealing with. So how is this telescope, your telescope or these observatories get the data from these far objects?
FRBs were first discovered in 2007 at West Virginia University, where I'm doing my PhD from. Since they are so bright, we can observe them from galaxies outside of Milky Way. Because of the gravitational force, these clump together to form stars. When this burning stops, there is nothing to prevent the gravity from collapsing the star. So the star will crush under its own weight, and then it will explode. So like you said, I also believe that they exist, because otherwise it will be so self-centered to think that of all the trillion star system we are the only special one. I don't think that's true.
Okay, you are studying this physics for quite a long time now. It's almost 10 years. Astrophysics is the crush for all the physicists enthusiasts from the very beginning. But the key point is that we should keep up the curiosity to be in the research, right? And how was your journey? How do you keep this curiosity?
Astrophysics is a postgraduate degree, so my advice would be to find the people that you want to work with. It's a male-dominated group, so it's hard, but you have to persevere through it.
So hi everyone, welcome back to my channel. Once upon a time, when we were introduced to these galaxies, stars, and all this universe by our science teacher when we were very young, that opened a new horizon to most of us. And astrophysics was actually a crush for most of the physics enthusiasts from very young age. And today I'm really excited to introduce an astrophysicist, Reshma and Thomas, who passionately pursuing or follows the voice of the stars for quite a long time. And I should actually talk about her CV, then you will understand how important that she is for this particular discussion here. She is currently doing her PhD at the University of West Virginia in the United States of America, where she is studying this radio transients, which we will come to know in this in the upcoming time. Also, she completed her bachelor's and master's as an integrated course from the University of Pondicherry in India, where she was studying about this radiation detectors with carbon nanotubes, where she was also a gold medalist at the university. She also have quite a lot of research experience in India itself. Notably, she did some internship in Indian Institute of Astrophysics, Indian Academy of Science. These are like prestigious institutes in India. So in overall, she has already like 10 years of experience in this particular field, right? Currently, she became, I would say, she's a little bit famous after her science publication. If you are in science, how famous you will become when you have a science article with the first author. And also, she gave invited talks in many prestigious institutes, notably in one of the department in NASA and also one of the departments in Caltech. So I'm really excited to have you here for this particular discussion. Now I invite you to this talk.
Thank you, Ranjit. Thank you for inviting me.
Welcome, and really I'm excited that we'll be having quite an interesting discussion on the birth of the stars, how do we detect the signals from there, right? About different magnetic poles and how the universe is expanding. This will be quite an interesting. I'm waiting for this.
Yeah, thank you. Thank you for the opportunity, and I'm really happy to share my experiences with you.
So PhD is actually a very narrowed down topic, right? Like peak of an iceberg. So for the general audience, could you explain exactly what you are doing?
For my PhD, what I'm studying is something called fast radio transients. So these transient events are some of the dynamic events in the universe. And when I say fast radio transient, it means that the signal that we observe from these events lasts for less than few seconds. So that's why the name fast. And radio, because these are observed in the radio wavelengths. So that's what I am trying to study. And I can give you a few examples of it. One is the pulsar emissions, which is so there are neutron stars, which are basically the dead remnants of massive stars. So when these neutron stars rotate, they can emit radio emissions from their poles. And if that emission is along our line of sight when they rotate, we can see them as pulses at their rotational period. So pulsar emission is one example of this fast radio transient. And another example of this radio transient is something called fast radio burst, or FRBs as we call it. So FRBs were first discovered in 2007 at West Virginia University, where I'm doing my PhD from, by Professor Duncan Lorimer and his undergraduate student, David. So these FRBs also last for like few milliseconds. So the data is only in few milliseconds, but they are so bright that they emit the same amount of energy that the sun emits in time scale of weeks. So in that 3 milliseconds or few milliseconds. And since they are so bright, we can observe them from galaxies outside of Milky Way. So there has been observations of FRBs from galaxies that were there when the universe was half its age. So it travels so far because they are so bright.
It's pretty interesting. So you are measuring something which happened many years before in small second with huge energy. That's so interesting. You mentioned about this life of a star. So about this neutron star. So then maybe people will be interested. How is a life of a star? Maybe in simple sense, how is the birth of a star to the death of a star? How does it look like in a scale, in a time scale?
Yeah. So in time scales, so stars can form from these gases of dust and clouds of gas and dust, and these because of the gravitational force, these clump together to form stars. And when the gravitational force is even stronger, this will start some nuclear reaction in the core, and that is how we see the star burning or shining, as we call it. So this nuclear reaction is typically some hydrogen fusing into to become helium or to carbon. So it depends on the mass of the star. And depending on the mass of the star, sometimes this burning, the atomic burning, can happen so quickly in terms of astronomical time scale. If the star is so huge, so massive, like I don't know, many times the mass of the sun, it can this burning can finish in matters of 1,000,000 years. So if the star is smaller than the sun or equal to the size of the sun, then this burning can go up to 1,000,000,000 years or a few billion years. So in the case of massive stars, the very big stars, this burning, when this burning stops, there is nothing to prevent the gravity from collapsing the star. So the star will crush under its own weight, and then it will explode into a supernova.
That's a death.
And become a neutron star or the black hole. But in the case of stars like our sun or stars which are even smaller than the sun, this since they are not that massive, this gravity cannot crush the whole star. So it becomes like a white dwarf, or it becomes a white dwarf.
So now I got some terms: white dwarf, neutron stars, plasma. So we will add this in the continued discussion. Now our main task is to observe this from Earth, right? That is what you are doing. And telescope, from every people know the telescope, we can see things from very far. But these are not light which are visible, what you are dealing with. So how is this telescope, your telescope or these observatories get the data from these far objects? So how does this telescope work?
Let's say this FRB was produced when the universe was half its age. So let's say it was produced on the surface of a neutron star, and this radio waves that is emitted from the neutron star will travel through the host galaxy, and then it will travel through the medium between the galaxy, between different galaxies, which is called the intergalactic medium. And then it will take, many million years to travel to the Earth. And through the gas and dust of Milky Way, it reaches the Earth. And on Earth, we have our telescopes, which is pointed at the source. So the telescope electronics is such that it can detect these very faint radio waves, and then it will record the data. And yeah.
And how do you know that this is in this direction? Now I'm thinking, if we are putting the telescopes here, how do you know that, okay, we should put it in this direction, I should put it in this direction? How do you know that where should we keep the telescope or point the telescope to?
Yeah, so there are different things to consider here. One, that the telescope time is very expensive. So we should have some prior information about where these things can occur from. So that prior information is important. So theory predicts that, okay, if we look at this point, you may see a pulsar, or the source that we are observing. So having a prior information is important, but in the case of FRBs, we don't know what exactly is producing them. So we don't know where it is coming from. It can happen anywhere on sky. So for the case of FRBs, like a targeted observation is not very useful, because we cannot say that it's totally unpredictable there.
So can I say that this is like similar to this neutrino radiation or muon radiation, which wherever you put, you can get, okay, now I got it.
Yeah, something similar. Yeah. So in the case of FRBs, there are blind surveys, which means that you look at some part of the sky blindly and you may detect you may detect it, you may not detect it. And there are other telescopes which have come in the last few decades, which will point to the sky, to a large part of the sky all the time. So these are stationary telescopes, and just as they will just look at the sky.
And what do you measure? What exactly measure? For example, if you have X and Y axis, what is in X and Y axis?
X will be the time and Y will be the frequency.
So you measure the time versus frequency, and what do you get? The information?
We'll get an intensity
plot, how it varies with different time.
So if in the case of FRBs, it should be like a straight line at one particular time, because it's the time duration is in milliseconds, so it should be like a straight line. But as I said before, since it travels through all these different mediums, like the intergalactic medium, through the gas and dust of Milky Way, all that, since these are radio waves, they undergo like a frequency dependent time delay, which means that the 8 gigahertz, let's say the 8 gigahertz part of the signal will arrive at the telescope a little earlier than the 1 gigahertz part.
So there is some error bar, an error bar. Can you distinguish it easily to confirm that this is exactly from this star or this is exactly from here?
Yeah, so that is possible with something called an interferometer. So interferometers are multiple telescopes. Yeah, but in radio it will be like multiple antennas um, that will point to the same direction. So because of this huge baseline, we know that from the single slit diffraction with baseline, the resolution will be very accurate, like small. So with this huge baseline, we can accurately point to where exactly it's coming from in the sky. Yeah.
Cool. We will be very interested in to know what are the biggest telescope in the Earth? What are the most common telescope or famous telescope? So we will be a little interested, right?
Yeah. So biggest telescope. So radio telescopes are typically the biggest in sizes because of what I said, the uh, angular resolution that is required for these astronomical observations, because we need to know where it is coming from, and it is so the equation goes like lambda by d. So lambda is the wavelength divided by the diameter. So for radio wavelengths, it is like it's very large, right? Meters or centimeter wavelengths, and in that case, we need a huge dish for that small angular resolution. So we need to find out where exactly it's coming from. So because of that reason, radio telescopes are the biggest, and the biggest radio telescope on Earth currently is the 500-meter aperture telescope in China, which is called the FAST in China. And there are other big radio telescopes are the Green Bank telescope in West Virginia, and there is one in Germany called the Effelsberg telescope, which is also like a 100-meter dish.
Oh,
Yeah,
I should check that out.
Yeah, you should definitely. It's gonna be amazing. So it's like a 100-meter dish. It's huge, and so those are the big telescopes, like in sizes, and like I said before, there are interferometers, and I don't know if you have seen. You would have definitely seen the images of the black hole. Which was released by the
3 years. Yeah.
By the EHT collaboration. So what they have done there is this idea of interferometry. So they have created an Earth-sized telescope by using antennas in different parts of the Earth, and then the idea is that they correlate the signals from each of different telescopes pointing at the same direction and create an Earth-sized telescope.
The diameter.
Yeah, that's how they got the image of the.
So I can say that will be the biggest telescope in the Earth. Okay, let's keep it like that. And even though it is an interferometer, it
is an interferometer. The idea is to
and then I know that in our university there is some collaboration with the SOFIA aircraft. So rather than the one stable one, it's moving. So what is the difference between this one, which can be connected to an aircraft, or which can mobile observatory?
Mobile observatory. So I think the idea of SOFIA is similar, except that SOFIA is works in the millimeter wavelengths, so which is in the microwave regime. So the problem with microwaves is from the terrestrial observation, like from the ground, is that we have a lot of water vapor on our surface, and that can create a lot of issues in the data. So like the phases of the signals will change, like there will be refraction, and all that can mess up the data. So it is better to go above the Earth's atmosphere, I think, and observe this millimeter regime which SOFIA operates in. So
So
that's
this
why it is
different
flying around.
So these
Yeah,
different frequencies will give information of the origin. Okay, this is coming from here,
yeah,
this is coming from here.
yeah.
And how much microscopically you will get the information? I think that what you are doing will be completely macroscopic. That you know that this exists here at this location. In our case, in condensed matter, we deal with atoms, right? So we see the origin in atomic scale. Do you ever do that? Do you also see that, okay, this wave is generated from these stars, and let's look into the atomic behavior of these stars, what atoms are moving on, or how is it generated? So any group does that, or?
Yeah, so we cannot definitely observe it. We can only theoretically predict these things from what is observed. Like, okay, there is some observation in the gamma rays that is coming from this source. What could
Uh-huh.
the reason be? And that's how it is typically done. And so these neutron stars are uh, very special in that regards because it is just made of neutrons. Like the 90% of the matter
Yes,
in the
yeah.
neutron star is neutrons. So it is a very uh, special equation of not the state of
Uh-huh.
matter. It is that is in the neutron star.
So there
So
is no element basically. There is no elemental occurrence in any of these stars. Everything will be just either neutron or cannot be considered as an element. No.
neutron stars cannot be, but this kind of, oh, if you are asking about elements, then
Uh-huh.
yes, like studying the supernovae, like that will,
Mm.
supernovae produces all the elements that we see in the universe.
Yeah, yeah, yeah,
Or
yeah.
a binary neutron, when something like a neutron star merges together, all these will create lots of elements. So yeah, studying that, yes, there are so many people that does that, and they do spectroscopy of these observations, and whatever element is there, you'll see a peak at their frequencies.
Uh-huh.
So
So that can be even
yeah,
done without you need the elements. In our lab, we need the substance and we do the light and see, okay, this. So this can be even done in a
no,
far distance.
yes, yes,
Wonderful,
you can do
wonderful.
spectroscopy. Yeah.
And you mentioned about this theoretical calculation. What are the theoretical calculations which are done in? So you are an experimentalist. There will be a theoretical astrophysics. We know, okay,
Yeah,
this general relativity, or some people will be calculating. For example,
yeah,
Albert Einstein one predicted the black hole existed, right? Then we
yeah,
found it.
yeah,
So how
yeah.
much theoretical part is currently occurring in this astrophysics field? We can
Oh,
compare
it's
an
like
experiment.
50-50.
Ah,
Yeah, yeah. All the experiments require a theoretical basis, or vice versa. Like
because
how
experiment
it is.
is a very
Yeah,
big deal with money, right? We cannot just randomly
yeah.
set up something and go.
Not just that, we observers need someone to tell us what exactly we are seeing in our data. So that's mostly the job of theorists.
Uh-huh. Yeah, and now let's go to your science paper, right? So that is about the magnetic field reversal in the turbulent
Okay.
environment around a repeating fast radio burst, right? Now these are just random words separated for me. Now
Yeah.
you can connect.
Yeah.
So maybe you connect. Maybe starting with the magnetic field, that is a little fascinating, right? Earth also has a magnetic field. Everyone knows that some magnetic field's
Yeah.
effect is there. Maybe you can just explain in a broad sense about your science paper.
So we don't know what exactly is producing FRBs. We think that these are some kind of neutron stars, very magnetic neutron stars. And there will be some uh, magnetic field around the object. We think that. And how do we measure this? We measure this by uh, observing the polarization properties of this FRBs. So if the if the if the bursts are like highly polarized, it means linearly polarized, it means that there is some ordered magnetic field in the environment. And when we when this linearly polarized wave passes through a magnetized plasma, it will undergo Faraday rotation. So I measured the Faraday rotation of this FRB along on a time scale of many months, and I noticed that the Faraday rotation, one, it's the magnitude is very high, which means that the local magnetic field is very high, and it also means that and I noticed that this Faraday rotation was changing in time scale of months, and it was not just changing, it was reversing, which means that this magnetic field is not just magnetic field along our line of sight is not just varying, but it's also reversing. That means we are either seeing through a different line of sight now, or something very weird is happening in the environment of this fast radio burst source. So I used that to narrow down the environment of this fast radio burst. So we cannot, since these are from very far away in the universe, some gigaparsecs away. So this FRV was some gigaparsecs away. So we cannot go and see what's happening near the environment. So I use this polarization information as a probe to the local environment, this variation in the polarization information as a probe to its local environment, and say that, okay, this is varying so much, this quantity is varying, this quantity is varying, which means that something around the environment is varying, and this variation could be because of this FRB source in near a binary star, because the wind of the star can create such environments near this FRB. Yeah.
Is it a first of a kind, or any other people also did similar Faraday rotation measurements for other other stars?
Yeah, Faraday rotation measurements are done for FRBs and for stars and like all.
This is a very interesting thing, because I thought, okay, we do that. Okay, when we apply time reversal symmetry is broken in some materials, we get Faraday rotation. Well, this is fascinating. And then also, now you mentioned about this reversal of magnetic field. Then I was wondering, I read somewhere that the Earth magnetic field can also be reversed at some future time, right? Is it true, or will it happen?
I don't know. Maybe it changes. I'm not like an expert in
How
that.
How is the magnetic field generated in Earth?
It's the core has this molten state of iron, and
Yes.
that when the Earth rotates, it rotates, and that creates
A magnetic field. Is it
yeah,
okay? Somewhat similarly in the stars also it generates, and
yeah.
so magnetic field plays a huge role in all the.
Yeah, it does. Yeah.
Wow, fascinating. And I also noted that your group also does work with this gravitational waves, right? This ripples in space and time. And is it a sound wave or a light wave? What kind of wave is that? And how do we measure with this LIGO observatory?
It's neither sound or light wave. It's an entirely different class of wave called the gravitational wave. And just like we have different frequencies in the electromagnetic regime in the light waves, like we have radio, we have visible, we have ultraviolet, all that different frequencies, we have similar frequencies in the gravitational waves too. And LIGO here on Earth measures the gravitational wave in the frequencies, in the high-end frequency spectrum, so the high frequency. My group at WVU works on the lowest end of the gravitational wave spectrum. So they use something called the pulsar timing array.
And so this LIGO in your group is not an interferometer, or is it similar to that interferometer?
So it's not exactly an interferometer, but they use pulsars, which are like extragalactic, like not extragalactic,
Uh-huh.
the extraterrestrial sources as their detector. So they
Hmm.
use this array of pulsars to detect this gravitational, low frequency gravitational waves that is present in the universe. So how they do that is that they measure the time of arrival of each of these pulsar regularly. They did this for the last 15 years, and they notice, so when a gravitational wave passes through these pulsars and through the earth, there will be some change in the arrival time of the pulsar signals to the earth because of the stretching and squeezing of the uh, space time. So they measured that change in the arrival times, and this change can be correlated, like it depending on where the pulsar is in the sky. Some of it may be correlated, some of this may be anti-correlated, this changes, and they measured that change, and they were able to measure this correlation that was predicted by theory. And yeah, so it took 15 years to for them to arrive at this.
Wow. Now I can imagine how lengthy are your experiment. In 1 year, you dedicate 6 months or 3 months properly for the experiment. Rest of the time you will be analyzing. You have to get this beam time or this observatory time. You go there, right? Do the experiment. So very, very, very lengthy processes.
Yes.
Excellent. And I also now was wondering, so 15 years of an experiment means the paper published at the end will have how many authors? One full page.
Oh yeah, I'm not sure how long the author list is, but yeah, it is also not just the like the North Americans. So
Uh-huh.
North Americans have this collaboration called Nanograph.
Uh-huh.
So this same work is done in Australia by the Parkes Pulsar Timing Array, in Europe by the European Pulsar Timing Array,
Mm-hmm.
in India also has started now the Indian Pulsar Timing Array,
Mm.
and there is also a Chinese. So all these separate collaborations published separate papers on this
Wow.
detection,
Oh yeah, I see. I see.
and sometime in the future they will come together and publish their
New
combine
discovery, a
their
wonderful.
results, yeah, combine the data and publish together.
I think now the technical part is almost ready. Now we know the most of the technical part. Now let's go to the stuffs which the audience will be much more interested, or the general audience will be interested. So when they want to speak with an physicist, they will be okay about black holes, about the universe is expanding. These are all already done stuffs, right? Already discovered stuffs. One of the main other question will be, does aliens exist, right? I also believe that they do. But if so, how do we, how, from your observatories, how do we know? How do we get the signals from them? Like, your take on these
Yeah,
aliens?
yeah. So yeah, like you said, I also believe that they exist, because otherwise it will be so self-centered to think that of all the trillion star system we are the only special one. I don't think that's true, but detecting them is a challenge. But there has been a lot of work going on, especially by the SETI Institute, which is the Search for Extraterrestrial Intelligence. So SETI Institute uses many telescopes. One such telescope is the Green Bank Telescope here in West Virginia. Um, they they have dedicated time on GBT just to look at millions of stars in the Milky Way to detect any kind of signals that we don't think is from an astrophysical sources, because as far as we know, astrophysical sources generate signals um, that can be somehow predicted by the theory. Like okay, these are the processes that can create an astrophysical sources. So the idea is to look for sources, look for signals that cannot be predicted by the physics.
Oh yeah.
I think that's the idea. Yeah.
Oh,
So
it's cool. It's cool.
there are work that's underway which looks for like millions of stars in the Milky Way to detect something like that. Yeah.
Oh, yeah, cool. And then maybe okay, you were studying this physics. Oh, yeah, cool. And then maybe okay, you were studying this physics for quite a long time now, right? Almost 10 years. And of course, as I told in the beginning, this astrophysics is the crush for all the physicists enthusiasts from the very beginning. But the key point is that we should keep up the curiosity to be in the research, right? How was your journey? How do you keep this curiosity?
Yeah, I was always curious about astrophysics, about stars and the physics behind it and the math behind it. So I think people people like astrophysics because it's very glamorous subject. You can see very pretty images from all these observatories, but it's not just about images only. I think people lose interest when they hear about the math and the physics that goes behind the subject.
And what advice you will you give for the people who are the students who are really motivated to pursue their career in astrophysics?
Yeah, so
From a school standard, from very young age.
yeah, from a very young age. So astrophysics is a postgraduate degree. So you should make your foundation strong by studying physics or engineering or mathematics or something related. So make a strong foundation, and meanwhile also try to do internships or projects in some nearby institutes in the field of astrophysics or astronomy or whatever, some small projects, just to keep that curiosity alive, and but at the same time study physics and finish the degree, go to a master's or a PhD program for astrophysics.
So you are saying that okay, we take a bachelor's course which gives you the foundation, then you do a master's, and then you go for a PhD. It's like that. And it's better to do this integrated course as you did, because many nowadays in India or in many countries this integrated course are booming. So is it better to be in an integrated course, or let's just do some bachelor's and then?
It depends. Like integrated courses, since you don't have to worry about. In the case of India, since you don't have to worry about changing colleges after 3 years, it will give you one full stretch of 5 years to work on your research project or whatever. So if you want, you can start your research in your second year or third year and then just continue that for 5 years. So it just gives you the continuity. That's the only uh, advantage of doing an
Just be in it,
integrated
right? Just
course.
be in it and go on,
Yeah,
right? Just be
yeah,
motivated and
yeah.
go on. So, considering the different countries, how much this USA is playing a role in this astrophysics for an educational viewpoint? Is it better to do a PhD in India or in US or in Germany? Where is the best place to do a PhD in astrophysics?
Uh, like astrophysics is uh, everywhere right now. Like wherever you are, it's prominent in India right now. It's very prominent in the US for the last many decades. In Europe, it's really great. So there are really great people in every continent, at least, who is working on astrophysics. So my advice would be to find the people that you want to work with, contact them, and work with them. Yeah, the people. Yeah, yeah. Yeah, so I was saying it doesn't matter where you are doing your PhD. It matters what you're working on and who you are working with. Are you comfortable in that group? Are you happy in that group? That's the
Cool,
important part.
cool. And also, I would see that in physics, at least until I studied till this much, there are very few women in science, right? Even for the Nobel Prize, it's only very few. But this year we got a Nobel Prize for a woman. So, how was your
Yeah.
journey in consideration with the woman in science?
Uh,
What would you say to the
yeah.
girls who are who are interested
Yeah.
in this science field?
I know there are so few women. Like my undergraduate classroom was dominated by male, and even in my PhD, uh, not in my group, but my cohort, it's a male dominated uh, group. So it's it's hard, but you have to, persevere through it. And to all the girls out there, just dream big and don't stop believing in yourself. I wish I could tell this to my younger self,
Aha,
that
aha.
not to stop believing in myself. So don't stop believing in yourself. And if you need help, just ask people. Everyone's so
Correct, correct.
helpful. So don't limit yourself. I think girls are typically taught to limit themselves. Like, don't think that
I
you
see.
cannot achieve it. There is no way you can do that. So, girls are, at least in India, we are typically taught to limit ourselves. So, just don't do that. Dream big, and you can
Excellent,
achieve
excellent.
it.
Even
Yeah.
you are one of the inspiration for me from very, very long
Oh,
time, right? You know,
thank you.
because we studied in the same school. I mean, for the
Yeah.
audience, and we had a same physics teacher, this Joseph sir. You
Yeah,
remember, right? He
yeah,
was
I
our,
know, I know.
the
He was my, yeah,
the
he was my very first inspiration to pursue physics.
that's absolutely. And then he introduced me to you, and then it went on. So you are a real
Nice.
inspiration for me also. So it's very nice that
Thank you.
I had a cool
Thank you.
discussion with you, and this will
Yeah,
benefit a lot of people out there, right?
yeah, I hope so too.
Then thank you.